9 o'clock exactly, so we'll go ahead and get started. Welcome to day 4 of BioPACIFIC MIP Summer School. Hope you've been enjoying the program to date. If you've missed any of the sessions, the videos have been posted on the Summer School website, so be sure to check those out. We are looking to finish the Summer School this week strong, and easy to do that with our next speaker, Professor Brad Olsen from MIT. As a means of introduction, Brad got his PhD at Berkeley with Professor Siegelman, who's now here at BioPACIFIC MIP and UC Santa Barbara, did a postdoc at Caltech, and then started at MIT as a professor in 2009, where his group is focused on polymer, biopolymer synthesis, characterization, modeling with an eye towards functionality. But the group also has a big effort on AI and automation, right? Brad's been leading an effort on Big Smile's informatics nomenclature for polymers, which is being integrated into the new NSF Convergence Accelerator Program, CRYPT, which is an effort on really creating a big database for polymers. And as you have seen throughout this week, data in this space is absolutely critical, organizing it, figuring out how to set it up so that it's mineable. So I think very excited to have Brad here to talk to us about the complexities of doing that, especially with polymers. So Brad, the floor is all yours.
Thanks, Tal. Welcome, everybody. Let me get my screen shared here real quick. It's a pleasure to have a chance to, I guess, visit virtually and speak to you all today about some work in standard representations for polymer data. I want to start by acknowledging a bunch of folks who've contributed to the development of our piece of the work here today. Members of my own lab, Tishang Lin, Haley Beach, Hidenobu Moshigase, Nathan, Akash, Dylan, and then also a bunch of collaborators, partly through the MONET, the CCI, NSF CCI Center for the Chemistry of Molecularly Optimized Networks. MONET is the grant that has supported the work on development of Big Smiles, and then also partly through the NSF Convergence Accelerator Program, which has supported some of the work I'll talk to you about on search today. So I want to start by highlighting, I think, 2 key trends in science and technology that have probably permeated a lot of this summer school. And one is that sensors and electronics have gotten a lot less expensive, making automation increasingly affordable. Basically, people are now becoming slower and more expensive than robots for doing a lot of tasks that previously we thought would be, the domain of people for quite some time. At the same time, models and algorithms for empirical data modeling have grown increasingly capable and accessible. So these things together mean that it's possible for us to generate lots of data. And if we can generate lots of data, and if we can organize it in a way such that it is analyzable, it's possible for us to analyze and gain insights from that data using lots of new powerful tools. And so I think that these 2 sort of scientific trends, which have been decades in the making, basically cheap sensors and electronics and advanced statistical models, are converging to give us this sort of data-driven era. And this has, I would say, this is something that's already largely blossomed in many areas of chemistry and materials science. The Material Genome Project that started out at MIT, I guess, several decades ago, and really inspired the Material Genome Initiative, is something that's a very well-established project in inorganic materials in terms of cataloging the properties of huge numbers of materials. And then, it's also become very popular to use informatics and chemistry for things like catalyst design or pharmaceutical design. And small molecule chemoinformatics has advanced dramatically. And so I want to pose a question: why hasn't data-driven research impacted polymers to such a degree that it's impacted other areas? And there are a few fundamental issues with polymers that have made data-driven research kind of difficult. The first one is that polymers don't have unique chemical structures, right? Those of you who are history buffs will recall, that we are just past the 100th anniversary of Staudinger's very famous paper reporting, arguing for the discovery of polymers as large molecules. And The fact that a large molecule could even exist was controversial for an extended period of time. And a large part of this has to do with the fact that there's no one unique polymer, there's no one unique molecular structure for a polymer. The data on these materials tends to be in lots of small data sets. And there are really serious challenges with nomenclature, right? So if I say I made something out of polyethylene, right, that actually doesn't tell you a whole lot about what I did. It tells you a lot about what I didn't do, but it's not, there's no way you could reproduce it if you know I made it out of polyethylene. On the other hand, if you know I made something out of ethanol or caffeine, two of the more popular small molecules for grad students, you would know exactly what I had, right? So this is a big nomenclature issue, and organizations like IUPAC have worked to address this, but the problem is largely unsolved. And if you read, academic papers, I think papers many of you publish, the nomenclature systems are ad hoc, I guess is the best word to describe it, right? A lot of polymers are described as 3A or, PNB 72 or something like this, right? There's very little information that's not dependent on the context of the paper in that type of name. Right? This makes it hard to look stuff up because we don't have a functional system for naming and searching that people widely adhere to. Polymers have multi-scale chemistry and physics. And so what sort of length scale of description is necessary to predict properties is challenging. And in particular, lots of properties don't depend only on chemical structure. For example, the crystallinity of a polymer doesn't depend only on its chemical structure. And this can make it tricky because the chemical formula is not enough to fully describe the polymer material. So a lot of these things, really the challenge centers around how we organize and sort and share and compare and combine our data about the research that we're doing. Or maybe I could rephrase, a lot of these challenges center around difficulty we have communicating with each other, because we don't have necessarily clear, organized ways of communicating with one another. We publish scientific papers and we read those, and this is actually kind of a slow, inefficient process of transferring material. And I would say, you could probably characterize this photo as accurately describing the current state of polymer data, right? There's a lot of it. We've been studying these for 100 years, right? Good luck finding the data that you need, even if it's already been generated. I don't know how many of you in the room, nobody needs to volunteer or commit to this, but I would guess that some of the PIs maybe have had a student leave and had trouble finding data afterwards. I would guess that there's lots of new students who've called senior colleagues and been like, the PI told me that this exists, but I have no idea where it is. I would guess lots of people have read papers and found that there were things that seems to be incomplete or difficult to reproduce. These are all, at least in part, difficulties with the way we store, compare, standardize our polymer data. And so what I want to tell you about today is a very narrow slice, because I know this is summer school, so I tried to focus as much as I could on teaching and not zooming through stuff. Although it still might be kind of quick. So try to slow me down and interrupt if you feel the need. But I want to focus today on how we could standardize and better communicate things about chemical structure as a small piece of the overall efforts that Tal mentioned in terms of being able to provide standard databases for chemical structure. To illustrate the problem with the way we communicate today, and I guess before starting this, I want to say, I think originally, we thought that this was about data mining and machine learning. And I don't think it isn't about data mining and machine learning. I just think that data mining and machine learning is like the 1%. And the 99% is communicating with each other. And if you can communicate and share more effectively, that same sharing makes data mining really easy. But if we don't communicate and share effectively, then data mining becomes really hard. So I think if you're not a machine learning person, I hope this is still really interesting to you, because the talk isn't about machine learning. The talk is basically about how to communicate better with each other in terms of the research that we're doing. All right, so I want you to consider the following scenario that was developed by my ex-grad student, Jieshang. He's Taiwanese, not Australian, just as an observation. But anyway, so, he also doesn't do any experiments, but he imagines this is how experimentalists would talk. And I think it's a fairly realistic depiction of things that would actually happen at MIT. And so, someone invented something and the other person says, what did you invent? And they say, well, I have, I don't know what I call it. They look on Google, right? And then, okay, here's the name. 2-methyl-2,1-methylpyrrole 2-ylpent-3-enitrile. Right, that sounds complicated. And so how would the other person reply? I think you would all universally agree. They would say, what is that? They would maybe insert another more colorful word into that statement. Can you draw me the structure? Right, the bottom line is that we communicate chemistry through pictures. Right, we don't really speak chemistry very well. So here's a picture of this compound. It's actually not that complicated, but man, that's a horrible name, isn't it? This kind of illustrates the problem. We're not so great at communicating chemistry in this sense. And then, okay, you get it. Now here's the challenge. Computers kind of stink at pictures, right? They don't really understand images in the way that we do. They understand images as bits and pixels, right? So when we want to communicate a chemical structure to the computer, we use basically connectivity tables. And so here's a connectivity table for this compound extracted from ChemDraw. And if you're a human being and you look at I assume everyone on the call is a human being. So you look at this and you would probably say, my God, I have no idea what that is, right? That's very difficult to read. The computer loves it, but humans not so much. So, the name is a reasonable compromise, right? The IUPAC name is actually a reasonable compromise. Computers can handle strings really well, and people can sort of handle names, although we prefer pictures, until you consider the fact that globally we speak a lot of languages that aren't English. So here's the name of this chemical in Mandarin. Probably not too many people on the call that's very useful for. So the problem is language really isn't universal either, right? So none of these things, so I guess I would argue there's 3 criteria we need to communicate well in the data-driven age. We have to be able to talk to computers, we have to be able to talk to other people, and it has to be universal across all the different variations in language and region and this. Because if you can only communicate with other people who communicate primarily in English, you're restricting yourself to a tiny fraction of the global research community. So in small molecules, this problem has been solved using line notations. The idea of line notations is to take the very best of chemical structure drawings and represent them as strings. And these strings are independent of language. And these things, I feel like line notations are very intimidating the first time you look at them, but that they're relatively quick to learn how to speak. It's definitely much faster to learn how to speak than a foreign language. So I want to give a brief primer to probably the most popular line notation for small molecules, which is called SMILES, right? And you can look up what the SMILES acronym stands for. I won't try to introduce that because I think it's not super relevant to trying to understand what SMILES is and how it works, and everyone calls it SMILES. So the idea of SMILES is basically to represent chemical structure drawings with compact strings of characters that are readable by both human and machines. And so we can consider, so here's a few examples that teach you how it works. So starting with propane, what you see is we basically write all the heavy atoms explicitly as characters using their atomic symbols, and the hydrogens are left implicit. Moving on to 1-butene, when we have a double bond, the double bond is explicitly written, and you notice all the single bonds are implicit. Branching, is written with parentheses to denote a branch. Heteroatoms like oxygen use their different atomic symbol. Here in this, this is butyric acid. Butyric acid, again, has a branch for the carbonyl and a couple of heteroatoms. Rings are tricky, right? Because strings are linear and chemical structures can have rings. And so SMILES uses ring closure notation. So C1 denotes the first carbon. It can actually be any of these in cyclohexane. And it connects back to the other carbon labeled C1. So these two ones denote the 2 points that will close a ring, and an additional single bond is implicit between those 2 points. Toluene has the same thing and shows us as an additional feature, which is that aromatic atoms can be denoted as lowercase, and then the double bonds are left out. And so this gives us the ability to compactly denote aromatic rings. Triple bonds are with the pound, for example, in acetonitrile. Here we have a naphthalene with 2 different ring closures. It shows you how we can have multiple ring closures. And here's a terephthalic acid, kind of bringing it all together in a polymer context. Right? And so this is basically how the SMILES works. And it gives you the ability to represent each molecule as a deterministic string. And this has been fantastically useful in cheminformatics because now chemical structures can be easily processed by the computer and they can be stored in an extremely data compact way. Right? This allows you to index and search and analyze massive sets of chemical structures and use them in all types of different informatic tasks. Now, the challenge in polymers is that a polymer doesn't have a unique chemical structure, which means that if we try to write the SMILES for a polymer, we would never be able to decide which SMILES to write because there is no one choice for the atomistic connectivity of a polymer. Rather, our chemical structure drawings in polymers represent ensembles of molecules. Right, so this is the same, for those of you who like physical chemistry and statistical mechanics, this is very much analogous to the concept of an ensemble there. Right, an ensemble is a set of all possible molecular states consistent with the constraints of the system. So when we draw a chemical structure, such as in this case for a diblock copolymer, it's consistent with all the different states where we have block A followed by block B. But if we have block B, then block A, then block B, that's not consistent with the chemistry of the diblock copolymer, right? And so all of these first states would be in the ensemble and this last state would not. But the chemical structure doesn't tell us how many of each of these molecules we have. It doesn't tell us information about the molecular distribution, right? So when we're trying to capture chemical structures of something without a unique molecular distribution into a string, our goal is to define the ensemble. Right, define the ensemble of molecules. And to do that, Qiushang led our project in developing a variation on the SMILES language, which we call big SMILES because polymers are big. And so it's basically SMILES for big molecules. And the idea is to use the concepts that you use in your chemical structure drawing to represent polymers, but to adapt them into the line notation format. And it turns out there are only 2 types of grammatical element you have to add to SMILES to be able to go from the small molecules that we showed you to a polymer. The first one is we use something we call a stochastic operator, which we denote by curly brackets. So the stochastic operator denotes the piece of your chemistry that was done using a stochastic reaction, right? So this would be your chain growth or your step growth polymerization piece of the chemistry. Within the stochastic operator is a comma delimited list of repeat units, right? These are not the monomer, but rather these are the chemical structure of the repeat unit that is in the polymer itself, right? So this is the piece that remains in the polymer. And so there are potentially many different chemistries that could lead to the same final big SMILES structure, same final polymer structure, depending on the way you choose, for example, reactive end groups. The way you list repeat units can denote all kinds of different polymers. So you can have homopolymers, you can have statistical copolymers, you can have block copolymers, you can have alternating copolymers, or for example, AABB polycondensations. You can write branch copolymers, polymer networks, brush polymers using nested stochastic objects even. So if you allow these to be nested like an object in computer science, you can have sort of recursive systems to generate brushes and brushes on brushes and things like this as well, just using simple combinations of this stochastic operator. Now, within the stochastic operator, you have to add one other element, and that's you have to give the computer instructions on how the repeat units connect to each other. And this is done by something we call a bonding descriptor, which is a pseudoatom that represents the connectivity between monomers. And there are two types of pseudoatoms. One we represent with $, and this is for essentially a symmetric bond or symmetric connectivity. It doesn't mean that the two atoms forming the bond are the same, although in polyethylene they are. In ethyl vinyl acetate, they're not. What it means, though, is that any $, can connect to any other $, right? And so in the ethyl vinyl acetate, for example, you can have basically monomers going in multiple orientations, head to head or head to tail. And this is illustrated here with this example for vinyl chloride, where you can have potentially 4 different arrangements of 2 monomers, depending on the orientation of each of the 2 monomers. And all of these are potentially allowed within the ensemble for the polymerization. Now, some may be much more probable, right? This one is the most probable, but the other ones do happen with a finite probability. Other types of bonds occur between 2 different functionalities, each of which is not self-reactive. And so this is AB type bonding, and we represent this with the arrows, greater than and less than sign. And so, for example, here, if we have a polycondensation of a diacid and a diamine, or a diacid chloride and a diamine to form various nylons, this would be with arrows. Ring opening polymerizations, such as the polymerization of PEG. In these ring opening polymerizations, the ring, you can never connect 2 oxygens forming a peroxide. And so you get this preferential orientation denoted by the arrows. And of course, in things like peptides, where you essentially have an AB type polycondensation with the A and B in the same molecule, you also use these arrows, but now you have the 2 opposite arrows on opposite ends of the molecule. Instead of in the AABB, you had the same arrow on both ends of each repeat unit, denoting that this had the same functional group on both ends. Right. So this gives you just these 2 different types of forming bonds allow you to capture, at least so far, every polymerization we've encountered fits into one of these 2 categories. And so this gives you a very broad ability to capture polymer chemistry. In addition to repeat units, you also need N groups. And there are 2 ways to deal with N groups within Big Smiles. The first one is at the end of our comma delimited list of repeat units, we can add a semicolon and then have a second comma delimited list of N groups. And these are what we call implicit or non-deterministic N groups. The other thing you can do is you can simply write smile strings adjacent to the stochastic operator. And then these are deterministic or explicit N groups that are simply specified by string concatenation. Right? And so using this example of nylon, we can write this in 2 different ways. So here again are our diacid and our diamine monomers. And then we can specify that, for example, we could have an OH N group or just a hydrogen N group on the end of the polymer, right? And each N group has only 1 bonding descriptor, right? Because it doesn't polymerize, it's terminal. So this OH, of course, would correspond to if the last monomer were a carboxylic acid, and this H would correspond if the last monomer were an amine terminated monomer. Now, say we wanted to specify that we synthesize this polymer with only carboxylic acid N groups. So we, for example, added a substantial excess of the carboxylic acid to try to get into this state. Then one could explicitly write these carboxylic acid N groups outside of the string and have the stochastic operator inside. Now, in this case, there's a tiny wrinkle, and that's that we know we can never have an oxygen bonded to a nitrogen by this chemistry, right? So when you specify this end group, you're also specifying which monomer must come first in connecting to it. And to account for that, we include this bonding descriptor just inside the stochastic object. You see up here, it's there, but it's empty. It's unspecified. Here it's specified, and this gives instructions in terms of interpreting the big smiles to say that in order for this end group, this explicit end group to make chemical sense, you must first bond to the complementary bonding group to a left arrow. So it must be a right arrow coming first. It must be the carboxylic acid, right? So it gives you this implicit functionality to connect in a chemically meaningful way to the explicit end group outside of the system. With just these rules, you can actually do all kinds of really complicated stuff. So you can do stars, block copolymers, polyurethanes. I show lots of examples of that here. There's block copolymers basically have multiple stochastic objects in a row, right? In a diblock, in a triblock. Star polymers can have stochastic objects in branches. Polyurethanes have nested stochastic objects. So the pre-polymer, you may not think that a repeat unit could itself have a stochastic object, but it can. And so that's basically a pre-polymer by using stochastic object nesting. And so we take these just two additional elements, bonding descriptors and stochastic objects, and by using basically various ways of arranging them combined with the logical rules of smiles, you can produce all of these polymer structures effectively. Polymer networks are also very easy to do. There was nothing that limited you to only 2 bonding descriptors per repeat unit. And so when you have 3 or more, you can have monomers that form branch structures, and this can lead to polymer networks, hyperbranch polymers, and all these other types of branch structures. Tacticity can also be captured in a fairly straightforward way. So I show here examples for polypropylene. So in smiles, the ampersand symbol is used to specify the chirality of chiral centers. And so by specifying chirality within the repeat units, we can specify different tacticities of polymers using basically different representations of their repeat unit, right? So in the case of polypropylene, you really need this head to tail addition for the tacticity to have its meaning. And so in this head to tail addition format, you can get 2 different types of isotactic polypropylene, which are, I think in a polymer sense, chemically equivalent. And then you can also get syndiotactic when you have alternating chiral centers along the backbone, and we can easily code that in as well. Finally, I know at UCSB for sure, polyelectrolytes are super popular, and smiles contain support for salts. And so counter ions can easily be added to the polymers using smiles notation, just incorporating those counter ions into the repeat units. Finally, this is not published yet, but we're working on writing up an extension of Big Smiles that allows you to specify non-covalent bonds, because a lot of people in colloidal, supramolecular material chemistry use non-covalent bonds in order to program in their materials. And so what we now allow you to do in this modified version is to take your bonding descriptor and add after it essentially annotations that specify that the bond is non-covalent. And this allows you to capture hydrogen bonds, ionic bonds. I don't show any examples here of pi-pi stacking or metal coordination bonding, but they're all supported in the new non-covalent revision. And this gives you the ability, this is also very important for Monet, which is sponsoring the development of this, because there they want to capture physical networks as a key piece of the chemistry that they're doing. And physical networks rely on non-covalent bonds to do this. I think this is something that's really uniquely enabled by Big Smiles, because Big Smiles is already inherently writing stochastic chemistry. And what is a non-covalent bond? It's a bond that forms with a probability less than 1 in the molecule. And so Big Smiles is already set up to account for things that happen, but not with the probability of 1 by nature of its stochastic chemistry. And so accounting for these bonds and the fact that they form in some sort of fractional sense is very natural within this stochastic framework. So to emphasize that this really does help you communicate chemistry better, I want to show you an example of something that actually really happened in my lab. And so, when you try, I don't know how many of you try to communicate your chemistry on your cell phone, but I do a lot. You're trying to bang out an email or something like that. So, this doesn't work very well, right? How, typing chemical structures in, it's a pain to open up ChemDraw, export the images, incorporate it into text. I mean, to be honest, it's something I really only like to do if I'm trying to write a paper. Otherwise, I find this to be obtuse and burdensome. Wouldn't it be nice if you could bang it out as simple as tweeting? And to be honest with you, that's what line notation lets you do, right? So you can actually text this to your students or to your advisor. I would encourage you, text this stuff to your advisor, right? It's totally readable, not right away. You got to learn how to read it, right? But this is communication that my students and I and students in my group actually have with each other. And we actually find it's way more efficient. No one has to remember the acronym or the name that different people are using for different complex chemicals. No one has to try to look up an IUPAC name for a polymer that they don't know what it is. So I think this is absolutely fantastic for being able to communicate chemical structure unambiguously in these types of ways. Once you have this ability to sort of unambiguously represent chemical structure, then it lets you think of all different things you can do regarding not only sharing, but regarding search, indexing, and constructing databases around these sort of universal representations for polymer chemical structure in exactly the same way that people already have for small molecules. And so to help with the development of this language, we've launched on GitHub the Big Smiles project. And so we're very happy now that we've surpassed all of the dentists' offices on the Google search. We found out about that a few months ago. It used to be if you ever tried to find this, you would just get a lot of advice about your teeth. Now you can probably find this by Google searching as well. And this is a place where folks can contribute, comment, and help to develop this in a way that it becomes useful for the broader community. In particular, so when we first published the initial version of the language, there were a lot of comments on potential compatibility issues with various versions of Smiles. And so we published a second version of the language resolving all the people's concerns. And so that was fantastic. And now we're working on publishing all kinds of tools to support you in your use. So on this website, there's a parser that you can use that allows you to parse Big Smiles so that you can better use them in all kinds of analysis code. And something really cool is there's a Big Smile drawer based on the open source chemical drawing program Catcher. And so you can actually draw polymers in Catcher and then output the Big Smiles if you don't like the idea of having to learn to write the grammatical rules. This one's a little finicky because it turns out you have to actually draw the chemical structure correctly in order to get the right Big Smiles. And a lot of us, even in our own papers, have some errors in our chemical structure drawings. And particularly with things like random and statistical copolymers. And so if these things are drawn in error, then Catcher will send back an incorrect Big Smiles. But it's not a translation error. Usually it's usually an error in the way the chemical structure was rendered. But these types of tools are kind of growing, I guess, not by the day, but by the many tools are being added each year to hopefully expand the utility and the accessibility of this. I think the big thing we're working on that's not in there right now is an interface between Big Smiles and RDKit so that you can use Big Smiles in RDKit and use all of those tools that people are used to for small molecules. The last thing I want to talk to you about is just to show you, again, some work that's not yet published, but that we are heading towards, where we're very excited about the ability to do search, right? And so I want to start by introducing to you the search version for small molecules, which is called SMARTS, right? SMARTS is a way to specify queries that can be searched against Smiles structures. So I show here a few different queries. that can potentially be searched. And what smarts looks like smiles. So you might say these kind of look like smiles, right? This could be formaldehyde, maybe. This would be ethanol, right? But now when you're doing queries, these are all substructures, right? So for example, looking at the propane substructure, anything that has this sort of substructure in it could potentially hit. So propane could hit to this query, cyclohexane could hit to this query, the pentane isomer, even the 1-butene, right? It's got 3 carbons connected by 2 single bonds. The butyric acid would also hit to this structure, right? So the idea of smarts is that in the same sort of language of smiles, you're specifying a substructure to search against. And then basically you can search databases of molecules to identify molecules with that chemical substructure. And this provides an extremely powerful way to specify small molecule searches in line notations. And given the fact that polymer data can be so tricky to find, and that we have such problems with nomenclature, that name searching is really, really inefficient, we really need a tool like this to be able to search for polymers that we're looking for within the literature as well. And so we're working on putting the final touches on a big smart searching language. Actually, when I say final touches, what I mean is we're working on writing the code to actually do it, so that we can launch a program along with the grammar so you could actually run a search. So basically, this allows you to search for substructures just like you would in small molecules. So I show here 4 different polymers, and then I show a query on the left, and the red dots highlight where the query would hit in these polymers. Right, so if you just search, for example, for CCO, it would look for any CCO combination. So it would find it in PEG, it would find it here in the N group of this polymer, it would find it in the side chain of the polymer. Right, if we search for CCO inside a stochastic object, it looks for it only in monomers. So it ignores the N groups and searches only in the polymer pieces. If we specify the hydrogens, now this is going to eliminate things where some of the carbons, for example, were tertiary, right? Because we've explicitly specified that each of these have to be methylenes. So we hit to a reduced number of objects. And now if we add stochastic, if we add bonding descriptors, now this will only hit when the CCO is, or in this case, COC is found entirely within one monomer. And so you get a reduced number of hits. So the grammar, and there's lots more manifestations that we don't have time to talk about today that can get more advanced, but this basically gives you a way to do chemical structure searching in polymers by extending the small molecule smarts in the same way we extended the small molecule smiles. The way this works in practice, to get a little technical in terms of the algorithm, is we start with the query and the target. The query in big smarts, the target in big smiles, and we map both of these onto a graph-like structure known as an automata. And so these automata are basically computer machines that the machine, as you use the machine, it actually generates molecules that are part of the molecular ensemble, right? So our query CCO only has one query. And so we start at the starting point of the automata. And as we move from state to state, every time we pass over an arrow, we add the shown atom to the string. And so we would go CCO and have CCO. For this polymer, this is polyethylene glycol copropylene glycol. Right here, you could start. And as you go around the loops of the automata, you add CCO or CCO. And so you can add different monomers essentially as you go around the different loops. In order to then search whether the query is found within the target, we use the automata to generate trees of atoms, where every time you reach branch points, you basically, in the automata, you get branches in the tree. And we look for whether we find these atom series within the branches of the automata. And this basically gives you a method for doing search of these molecules by first mapping the molecule onto an automata graph, and then basically doing path traversal through that graph in order to try to find matches. So it gives you a way to reduce this problem onto kind of relatively simple computer science problem. And this is the code we're working on writing up that will implement this high-level algorithm. I show it here for more complex query. So you can basically have this more complex query. Now you're looking for these rings of CCO. And so again, you can find that same path within the tree of this more complex polymer. One thing that makes implementing this really hard is that you could even imagine querying empty sets. So say I write this query. The meaning of this query in our grammar is search for any diblock copolymer. It has two polymers separated by an arbitrary number of atoms. And so this is a pretty hard search to figure out how to code. And so things like this are kind of holding up the development a little bit, but we hope that we'll have this out and available for people to try within the next several months as a really robust search tool. So bringing all these things together, we are currently working jointly with University of Chicago, Dow, NIST, and Citrine Informatics, as well as many partners, including BioPACIFIC, in order to put together the Community Resource for Innovation in Polymer Technology, or CRIPT. And the beta version of CRIPT is available on the web, although I guess it would be the Delta version is being built in secret, and I'm told you'll have it around Labor Day. But it's never going to be put on the web. It's going to be kept secret for various data privacy and security reasons. But the beta version's on the web, and you can use it, try it, test out some of the features. The idea of CRIPT is to combine these ways of representing chemical structures with some new ways developed at MIT and Citrine Informatics for representing data on material synthesis pathways. And the key thing here is that material synthesis is actually a time-structured process. I think this isn't a surprise to anyone who does material synthesis or processing, but you basically take a parent or a starting material and you process it or synthesize it into a product or a child material or a derivative. And so this process means that data should be organized in a structure known as a directed acyclic graph, where you have a molecule of interest and things are derived from that, but then it's also derived from other things and by other processes. And we naturally in our science use this relational reasoning. You know, for example, I made a polymer network and I made it of chains that had a molar mass of 10,000 grams per mole. Therefore, my molar mass between crosslinks is 10,000 grams per mole, right? You didn't actually measure that on the network. You measured the polymer you used to make the network and then made a property inference due to your knowledge of essentially the relational structure between materials and their children. And so this directed acyclic graph essentially captures that informational knowledge. And we published an initial version of this, PolyDat, I think earlier this year, maybe in like February. And now CRIPT has developed a more advanced version, which is the CRIPT data structure, by merging PolyDat with data schema from Citrine known as GEMmed, which is GEMmed, I don't think is published in the literature, but there's open source information about it online. And the combination of these two gives you a very robust platform for representing both polymer synthesis and processing data in relatively simple schemas. And so here's an example from my postdoc, Dylan, where he named his experiment Dylan's anionic polymer. He takes in some different reagents, solvents, has a reaction, makes a final product. That final product is characterized, for example, by mechanical testing and by GPC, right? And the arrows are all pointing backwards because you as a researcher are probably interested in Dylan's final product. But when you find this final product, you'd like to understand how it's made. You'd like to understand what it's made from. And so we capture this sort of backflow of relational structures to allow people who find the product to access all of the data that flowed forward into the function of that product, and also to access the measurements. And so this gives you this is sort of the core of CRIPT. CRIPT has lots of other stuff. Again, the search tools, the chemical structure tools, drawers, data plotters, things like this to help people do their work. But the key thing is this concept about how data should be organized in order to very efficiently find it, search it, and analyze it, and in order to understand how the information flows. All right, so with that, I'll end. Thanks everyone, and I would be more than happy to answer any questions.
Thanks, Brad. That was an incredible talk. Very much appreciated. Folks, go ahead and post questions in the Q&A, but we have one already to start. Adam unfortunately had to take off, but we'll record the answer for posterity. He's asking, do you have any guidance on best practices for learning this new language, specific techniques, exercises to streamline this? And he's basically going on the assumption that Duolingo hasn't come out with a Big Smiles module yet.
Yeah, that's a good question. So we haven't made a workbook yet. Maybe we should. But we actually found one of the best ways to make sure you can do kind of common stuff is we went to Joe Bisserano's book on predicting polymer properties, which I think to us is Joe Bisserano was way before his time, right? Today he would be viewed as a machine learning visionary, but back then, it just wasn't the same. But he's got a huge table of polymers in his book where he lists data for them. So we converted the entire table into Big Smiles. And in the SI of our paper, the whole table is published with all the answers. So I would recommend trying to convert his entire table yourself. and it's about 400 polymers. So that's a lot of practice exercises. They're not super complicated. They're statistical copolymers, AB condensations and things like that. But it really gets you a lot of familiarity with how you represent the different atoms. And I actually did it myself to check my students' work while I was sitting in the airport lounge in Dulles. And I think it took me 5 hours to do the whole thing. So it's not an insubstantial time commitment, but it's good practice.
All right. Some questions popping in on the Q&A from Yuning. While Big Smiles defines a set of possible structures, can it also describe the size and distribution of the molecules? How do you convert Big Smiles to formats that can be used by machine learning models?
Yeah, good questions. So let me see if I can break off both halves. So no, it does not tell you the molar mass, but neither did your chemical structure drawing, right? So it's neither better nor worse in information content than the chemical structure drawing. It's in fact, as best as we can tell, directly interconvertible, right? So how do you get that molar mass information today? It's your characterization data, right? You have to measure a GPC and that gives you some information, or you measure a MALDI, or you do, God forbid, you do viscometry. Right, some of my students are actually doing that. Very painful, but you have to do techniques like that to get the molar mass. This is where PolyDat and the crypt data structure come in. So these allow you to organize your data and associate your data with the chemical structure in the same way you would organize and associate measurements with your chemical structure today. And the idea here is that by not only associating measurements that you made on, so people do this a lot in database. They say, here's my polymer, here's what I measured. But the idea of this directed acyclic graph is that a lot of the measurements you made on that polymer weren't actually made on that polymer. They were made on some other structure in the network of related structures. So like, for example, you measured the molar mass and then you post-functionalized it. And then you didn't measure the molar mass again because it wasn't soluble in THF on your GPC anymore. Right? I think this is a pretty common problem. So PolyDat and Crypt are really designed to let you handle those measurements and those inference-based measurements in a very efficient way. And that's the solution we put forth to do that linking. How do you get the data into a format for machine learning? So most of the machine learning algorithms, I'm guessing you're referring to, what they want is a vector of numbers representing the molecule. Right, so essentially you have to take the chemical structure or the Big Smiles, you have to vectorize it. And there are a ton of vectorization schemes for doing that. Correct me if I'm wrong, send me an email if I'm wrong about this, but I believe we have published code to do a simple tuples-based vectorization, which is at the same level as group contribution theory. And that is on one of the GitHub repositories related to this. And it'll do single atoms, atomic pairs, and atomic triples. So this is at the level of a lot of the stuff that groups are using in the literature, and again, at the level of group contribution theory, a lot of those theories. For doing things like Morgan fingerprints, RDKit fingerprints, we actually have some simple patches that can get a big smiles into those type of fingerprints. I'm happy to share if anyone wants to use it. It basically involves using the big smiles to generate a ring, and then we feed the ring into RDKit or into other code. That eliminates N groups and other complexities. We're trying to write code that deals with the full complexity of the polymer to do that conversion in RDKit to access some of those other vectorization schemes. I'm guessing that that's a few months out before we could post our version of that.
And I know we're getting into the networking session, but I think this last question by Mike Lake is quite relevant. So I'll take a little over time, right? Because half of BioPACIFIC is looking at the bio side of things. How do you see the interface between what you're doing in polymers and what's being done with proteins, right? I mean, are there systems already out there for proteins? Are you planning on extending this into that space?
Yeah, great. I mean, great question. So we of course love proteins as well, and the thought hasn't structures. So you can write them into big smiles, and you could even have variable regions in a sense, or bioconjugates, I believe, are included in our article on big smiles. For example, conjugating a polymer to a protein. The problem is the protein structures are huge. And so we actually have a summer student this summer, and I think she's wrapped it up now. I have to check on the status because she finished last week, who was writing a converter between single letter amino acid code and full atomistic resolution smiles and big smiles that could work with big smiles. And so what this would allow you to do is to take your single letter amino acid sequence from any sort of bioinformatics package that you're using. For example, your DNA editor, take your express protein sequence, drop that in, and have that automatically rendered as smiles that you could combine with your polymer to make complex materials. And this would make it really easy to save and read. And we'd like to expand this even further in the future with an app that could go in these types of materials databases. And when it encounters a piece that's a protein, it would automatically simplify it for you and report it back to you as single letter amino acid code. This is super, super conceptually simple. You just have to do string substitution, which there's a lot of code that has to be prepared to be able to do it well, and a lot of debugging that has to be done. But the first piece of that, just being able to convert the proteins back and forth so that you can kind of copy and paste them into the materials, we'll have that up pretty soon.
Awesome. Thank you, Brad. All right. I hope everybody joins me virtually and silently thanking Brad for a fantastic talk and great Q&A. So once again, appreciate it. And we'll see hopefully everybody over at the Zoom session for networking. Debbie posted the link in the chat. All right. See you guys in a bit. Thanks again, Brad.